We have been learning about the moment of a force or many forces. What we have learned so far is that the torque about origin O, so that I will indicate by this, is R I cross F I, where we are applying these different forces F 1, F 2, F 3 and so on about point O. We have also learnt that the torque is origin dependent. There is a very special case when the total force on the body is 0, then torque is independent of the origin, no matter about which point it is taken, it comes out to be independent. Then as a very special case of this, we define a couple moment which is nothing but two equal and opposite forces separated by a distance d. In this lecture, we study moment a little more. We will define the moment of a force or a torque about an axis. Then I will give you an example to show you what you have been learning in 12th grade and our definition is the same. Then we go on to discuss the different elements in mechanical systems or civil engineering systems and what kind of forces do they apply with examples. So, we are going to study in this case the moment of a force about an axis. Why this is important is, a lot of times, for example, you have situations where something is actually made to rotate about an axis, this axis of a rotating disc I may have fixed in ball bearings which are fixed in some place. In that case, no matter what force you apply on the disc, the only component that is responsible for its rotation is that in the plane of the disc. And then if you recall your 12th grade physics, you have been defining torque about an axis as force times the perpendicular distance of the line of force from the axis. Now, we will get more sophisticated now that we have mastered the vector algebra and so on, and define the torque about an axis in a slightly different manner, which I will show through an example is equivalent to what you have been learning. So, let us say there is a disc which is rotating about a fixed axis which is in the direction of unit vector n, and there are various forces working on it. Then the torque about the axis n is going to be equal to the dot product of n with respect to the total torque about, say, the origin O. Although I am writing origin O, the torque about an axis is actually independent of where this origin is taken, because it only depends on the perpendicular distance of the forces from the axis. So, this I can write as n dot summation I R I O cross F I, and to emphasize that this is really independent of the origin, I will write it further as n dot summation I R I. I have removed this index O cross F I. This is the component of the total torque along the direction of the axis, and this is what I will call the torque about axis, let us say n. If you really work it out, what is happening is, since the axis is fixed, it is held by certain forces. No matter what forces you apply on the disc, the forces generated at the point where the axis is being held are such that they will cancel certain the applied forces and certain components of them, and then only force that is responsible for the rotation of the disc about this given axis is that which is in a plane perpendicular to this axis, and more effective it is if it is farther away from the axis. This you know from intuition and from your whatever you learned in your 12th grade. In a similar manner, the couple moment about an axis is the couple moment tau dot n, tau about an axis. Exactly the same thing as a torque, because couple moment is nothing but a very special torque. Let us now see if this sits well with our definition of torque about an axis is equal to force in the plane perpendicular to the axis times the perpendicular distance of the force line from the axis. This is the definition you have learned in your 12th grade. So, as a simple example, let me take a disc which is free to rotate about the z axis. Let us say this is the x axis, this is the y axis, and z axis is coming out of the plane. Let the radius of this be 30 centimeters, and let me apply a force at point r is equal to 10 I plus 10 j. In x y notation, it is a point 10 10, a force which is, let us say, 30 I plus 20 j minus 10 k. So, I am applying a force at this point which is like this in the plane of x y, and it has a z component also minus 10 k. So, therefore, going into the plane of this board. The torque, total torque due to this force is going to be equal to r cross f. Again, I emphasize, recall from your previous lecture, that this r could be anywhere along the line of action of this force. Right now, we will take r to be 10 I plus 10 j. So, this is equal to 10 I plus 10 j cross 30 I plus 20 j minus 10 k. Let us work it out, and it comes out to be 3 I cross I is 0. So, 200 I cross j, which is k, I cross k is minus j. So, minus minus plus 100 j, j cross I is minus k. So, minus 300 k, and j cross j is 0, j cross I, j cross k is I. So, minus 100 I. So, this comes out to be minus 100 I plus 100 j minus 100 k. That is the total torque, but I want to find the torque about axis z, because this disc is free to rotate about axis z. So, that torque, so let me make the picture again. Here is the disc. The torque came out to be minus 100, let us see, this is minus or plus, minus 100 I plus 100 j minus 100 k torque vector. So, torque about z is going to be k dot the torque, and which is going to be minus 100 Newton meters. Minus sign means that this is pointing in the direction of opposite to z. Therefore, the disc would tend to rotate with the right hand rule in the clockwise direction. This is the sense of rotation of the disc due to this torque. So, torque about z is coming out to be minus 100 Newton meters. Let us see if this is consistent with what we have been learning in our 12th grade. So, the line of force along which the force is working is this. The force is 30 I plus 20 J minus 10 K. As I said earlier, the only component of force that is responsible for rotation about the z axis is that in the plane perpendicular to the axis. So, only these two components. So, it is only these two components or the force in the plane of x and y that is going to be responsible for the rotation of the disc. And therefore, first thing we do is for tau about z, we ignore this force, the component of the force along the z axis. It cannot apply any force about the z axis. So, tau about z is going to be given rise to by 30 I plus 20 J. What is the magnitude of the force? It is 30 square plus 20 square. So, that comes out to be 900 plus 400, that is 10 square root of 13 newtons in this direction. I want to find the distance perpendicular to this force, that is this distance d from the origin. Let us find that. Let me make the picture again. So, as far as the rotation of the disc is concerned, a force is acting on this of the magnitude 10 square root of 13 newtons along this line, which is given by the vector 30 I plus 20 j minus 10 k. This we have ignored. So, in the plane x y, this is given by this. So, this line has a slope of 2/3 and it is passing through the point 10 10. Therefore, the equation of this line along which the force is working is y minus 10 is equal to 2/3, that is the slope, times x minus 10, and therefore, 3 y minus 30 is equal to 2 x minus 20, or 3 y is equal to 2 x plus 10. I want to find this distance along the line perpendicular to this force passing through the origin, and therefore, the slope of line perpendicular to the force line is going to be minus 3 over 2. Let me make the figure again. This is the disc, here is the force acting, and I am interested in this distance. The slope, the equation of this line is 3 y equals 2 x plus 10. Therefore, the slope of this line m is going to be minus 3 over 2 and it is passing through the origin. Therefore, the equation of this line is going to be y equals minus 3 over 2 x. The line along which the force is working is 3 y equals 2 x plus 10, and therefore, I can find out what the intersection point is. You work it out and you will find that x comes out to be equal to minus 20 over 13 and y comes out to be equal to 30 over 13. And therefore, this distance d perpendicular from the origin or the axis of rotation to the force line is going to be equal to square root of x square plus y square, which will be equal to 10 over root 13 meters. So, we have F, we have D, and therefore, the moment can be found out. The force is like this, whose magnitude is 10 square root of 13 newtons. We have found this distance, which is d is equal to 10 over 13 meters, and therefore, the torque about axis z is going to be 10 root 13 times 10 over root 13, which is 100 Newton meters, and because of the direction of force being this way, the sense is clockwise. This is exactly the same as we found earlier, which was coming out to be minus 100 Newton meters. So, you see the two definitions are consistent. So, let me now summarize what we have learned about torques. Torque 1 is equal to R I cross F I summed over. 2, torque is independent of origin if summation F I, that is the total force on the system, is 0. Third, that torque about an axis in vector direction unit vector n is n dot tau. Next, what we will do is, using the couple moment and force, we will like to transfer a force parallel to itself and see the effect of a force, how is it seen at some other point. For that, let me just motivate you by taking a rod. And apply a force here. If this rod is fixed here, what you will see is that this force will, number 1, push the rod in this direction and will also tend to rotate it like this. What I want to find is, what if I think of this therefore as a force pushing the rod in this direction, what else can it do? I will replace this whole thing by a force at this point and a moment that is rotating the rod. That is the total effect of the force. So, what we are going to learn is effect of a force at a point other than where it is being applied. Equivalently, in some books you will see this is called transferring force parallel to itself. And why this is important is, at times you want to really see the action of the force by describing its what all can it do. Can it rotate things, can it transport, can it move things, accelerate things, and so on. So, just in the example that I took, if I take a rod and apply a force here F, let us say the length of the rod is L and it is held at this point, and suppose the rod is in equilibrium, then you would say that I need to apply an equal and opposite force F in this direction, and because these two forces produce a couple, I need to apply a torque in this direction, which is of the amount F times L, to keep the rod in equilibrium. In other words, what I can say is that this force is absolutely equivalent to a force F at the pivot point and a torque like this of the amount tau equals F L and a force F. So, that if I want to keep this rod in equilibrium, I need to apply at this point a force minus F and a torque like this. So, this is equivalent to this as far as equilibrium or statics of this rod is concerned. How do I understand this? So, let me take a system and let us say it is free to rotate about this point, it is held here, and I apply a force like this F. Let me now add a 0 force, but a very carefully chosen 0 force onto this rod. I will apply a force in this direction and in this direction of the same amount as F, which is a 0 force, F in one direction and equal and opposite force at the same point. So, I have really done nothing to this, but now you notice that the original force and minus F give a couple, which is equal to the perpendicular distance between the forces times the force itself. So, I can say that this whole thing is equivalent to applying a torque at this point of the amount F d and applying a force F in this direction. What I have done is transferred the force parallel to itself to this point and consequently have generated, to keep the entire dynamics or statics the same, I had to apply an additional torque here. The effect of this torque and this force, these two elements, is exactly the same as the effect of that single force, original force applied here without these on the body. So, this is called two equivalent systems. It is easier at times to think in terms of couples and forces, and therefore, we do this. Let us take an example. You must have seen in buses the handle to change gears is of a funny shape. So, let us say if I take a handle in the xy plane of this shape, the gear handle, and this is the head where the driver applies the force and changes gear. So, let us say he applies certain forces and I want to know what is the equivalent system, how much movement does it generate at this point and what force is transferred here, and that is what we will do next. So, let us take the length of this part to be 60 centimeters, this part to be 30 centimeters and this part also to be 30 centimeters. Let this angle be 45 degrees, let this angle also be 45 degrees. And now we say that the driver applies a force F, which is equal to minus 5I plus 5j minus 2k, something like this, but coming out of the board. It has a z component also, or going into the board because z component is negative. A force like this to change the gear. What is the equivalent torque and force at this point? So, we are in a way transferring the force parallel to itself here, and consequently, we will indicate this force by an equivalent moment tau and a force F. So, let me make the picture again. Here is the handle of the gear, this is the gear head, this is 60 centimeters or 0.6 meters, 45 degrees, this is 0.3 meters and this is also 0.3 meters, and the force out here is minus 5I plus 5j minus 2k. The torque of the force is going to be R cross F. Equivalently, I can think of an equal and opposite force being applied here and force equal to the original force being applied at the bottom. I have done nothing but added a 0 force onto the system. Now, this minus F and the original force therefore, create a couple here, which is given by tau, and the force is the original force here. Let us therefore, calculate this couple. Either I can calculate the perpendicular distance between the forces, or I can straight away use the formula tau equals R cross F. Let us see what R is going to be in this case. it is going to be equal to 0.6 over root 2 I plus 0.6 over root 2 j, that is the vector from here, the first part of the gear handle, this vector, plus 0.3 I plus 0.3 over root 2 I plus 0.3 over root 2 j, and therefore, the total vector is 0.9 over root 2 plus 0.3 I plus 0.9 over root 2 j, and therefore, the torque is going to be equal to 0.9 over root 2 plus 0.3 I plus 0.9 over root 2 j cross the force is minus 5 I plus 5 j minus 2 k. I leave this as an exercise for you to calculate this torque, but once you calculate this torque, what you would find is this gear handle on which this force was being applied. This force system on this is equivalent to, on the same gear handle, as if we are applying a torque here of the amount calculated here and a force, the original force, which is minus 5 I plus 5 j minus 2 k. So, this sort of concludes an introduction to moments, couples, and finding equivalent force and couple systems given a force about a particular point. Next, we discuss different mechanical elements that are used in machines or structures and the forces, moments generated by these elements. Our strategy would be, I will take each element, discuss about it, and then solve a related example. The simplest of the elements is a string which can apply a tension. Suppose I am pulling a ball or something tied at the end of a string by a force F and it is not moving, then the string applies a tension in the opposite direction. But remember, a string or a rope can apply tension, but not compression. That is, if I instead push the ball the other way, the string would not be able to stop it. On the other hand, if I have a bar made out of a material, a rigid bar, it can apply both a tension as well as a compressive force. So, if I have a ball at the end of it, if I pull it by force F, it will apply a tension T if the ball does not move. If I push it in by a force F, it will apply a compressive force of the equal amount in the other direction. Next, let us discuss the contact force between a surface and say a rod or a box on it. So, for example, if there is a smooth surface and there is a rod here which is being pushed or whatever, and there is a box here, the only force a smooth surface can apply is perpendicular to itself, and therefore, it is capable of applying a force on this rod which is perpendicular to itself. Similarly, it is capable of applying a force on the box, may be distributed, may be at the same point, which is perpendicular to the surface. Why is it perpendicular? Imagine if it were not perpendicular, what would happen? Then this box, because of the component parallel to the surface, would start moving by itself. That does not happen, and therefore, we conclude that a smooth surface applies a force perpendicular to itself. On the other hand, if we take a rough surface, it can apply a force along the surface also, opposite to the tendency in which opposite to the direction in which the object has a tendency to move, and therefore, this would be direction of frictional force due to the rough surface, and of course, there is the normal force. Similarly, if there is a box and if I am pushing it this way, it will experience a normal force as well as a frictional force parallel to the surface. So, a smooth surface applies a force perpendicular to itself, rough surface applies a force which also has a component parallel to the surface. By similar logic, if I have a plank or a rod on a smooth on an edge, then the force on this plank is perpendicular to the surface of the plank due to the edge. Of course, the direction in this side would not be there. The only direction in which the edge can apply a force on to the plank is in this direction. If on the other hand there is some roughness, then there could be a force, frictional force in this direction also. Recall the example that we did earlier, where we had a brick on which I had a rod and I was trying to lift a weight like this, which applied a force downwards of 1000 newtons here. We realized that without the roughness here, the rod would tend to slip. Let me now do one example of this problem. Let us say I want to pull a roller. This is a very standard problem over a step like this. The height of the step is h and I am applying a force F in this direction parallel to this, and the weight of the roller is W, the radius of the roller is R. I want to know what force should I apply in order to take this roller over this step. Let us see what all can we do. So, let me make this again. I have this roller on which I am applying a force at the center to the right. This height is h, is being pulled down by W. Now, the possible forces on the roller, if the corner is rough, is a force like this, frictional force, and a force towards the center, the normal force. Then the force that we are applying F and the weight W. To find F, it is very convenient to take this point as the origin and balance torque about it. That would straight away give, in order for equilibrium, F times R minus h, because this distance is R minus h, is going to be equal to W times this distance, which if you work out is going to come out to be 2 R h minus h square. And therefore, the force that I apply should be equal to W times square root of 2 R h minus h square over R minus h. that should be enough to take it over the step. What about these forces, the force F and the force N? Let us calculate those also. So, you see now in this problem I am applying the torque equation first and the forces equation later. Let me make this big, and now we see that this force is W times square root of 2 R H minus H square over R minus H. This force is W, this force is N, and there is a force F like this. If I take summation over F x is equal to 0, then the horizontal component of the force F, frictional force, should balance the horizontal forces otherwise applied. So, I find that F, that is the force that we are applying, plus F, let us say this angle is theta. Cosine of theta should be equal to, if this angle is theta, then this angle would also be theta, because this is perpendicular to F and this line is perpendicular to this line. So, it will be minus n sin theta is equal to 0. And similarly, for the vertical forces, summation F y is equal to 0 would give me n cosine of theta plus F sine of theta minus W is equal to 0. These two equations are enough to determine small f, the frictional force, and the normal reaction N. Here, since this angle is theta, you can see that this angle is also theta, and therefore, sin theta is nothing but a square root of 2 R h minus h square over r, and cosine theta is nothing but r minus h over r. If we substitute these values in the equations, we find n is equal to W r over r minus h and f is equal to 0. So, this is a very special case where to take the roller over the step, you do not really need any frictional force on the edge. Notice that as r minus h becomes small, n goes up. So, therefore, the normal reaction keeps on increasing as h becomes larger and larger and larger. Compare this with the case that I discussed a while ago and also worked out in detail in the previous lecture, where we had a rod lifting a 1000 Newton weight. In that case, in order that the rod not slip over the edge, we had to apply, or we required a frictional force on the edge. So, what we learn is that a rod or a plank on an edge can apply normal force in the case of smooth surfaces, and a normal force and a frictional force when the edges and the surface are rough. Next, we consider an element which is a pin or a hinge, same thing. That is, if I have an element, a rod or a plank, and it is free to rotate about this point, it is hinged here. In that case, the hinge cannot apply any torque, but applies a vertical force and a horizontal force F y and F x. These are the only two forces that it can apply, nothing else. So, let us see an example of this. You have all traveled in trains, and sometimes when a berth is in its vertical position, you apply a force F like this in order to pull it up, and this is hinged at this point. So, the problem we want to solve is, suppose you pull this berth out and you are applying a constant horizontal force F like this. The weight of the berth is W and it is hinged here. I want to know the forces at the hinge. As I said just now, the hinge is capable of applying a vertical force and a horizontal force, F y the vertical force and F x the horizontal force. Then summation F x is equal to 0 gives me the horizontal force, and that gives me F x minus F is equal to 0 or F x equals F. Similarly, summation F y is equal to 0 gives me F y minus W is equal to 0 or F y is equal to W. Next, we want to calculate, given this force F and given this weight W, what is the angle theta that the berth makes from the horizontal. Let me make this picture again. So, this is the berth, you have pulled it out with force F, this is being pulled down by its own weight W, you are applying force F y and F x are being applied by the hinge. The length of the rod is L. There are torques, when I take torque about this point, being generated by the weight W and the force that I am pulling with. If I take torque about z axis should be 0, then the weight is giving a torque in this direction counterclockwise is going to be positive, and F is giving a torque in this direction which is negative. This gives, or let us calculate the distances first. This distance is going to be L over 2, this angle is theta, cosine of theta, and this distance is going to be L sine of theta, and therefore, when I put tau z equal to 0, I get W L over 2 cosine of theta minus F L sine of theta is equal to 0, and that gives tangent theta is equal to W over 2 F. You notice, larger the force that you apply, smaller the angle, and that you experience when you do something like this. You pull the berth out, it goes higher and higher and higher. So, this is an example of solving a simple problem using hinge forces. Next, we look at built-in supports, that is, suppose there is a support or a beam which is inserted in a wall and is like this, and I apply the load here in any direction, or a support which is glued to a wall. Suppose I glue it here, glue or weld. So, welded or glued support, and this is built-in support. What all are these capable of? So, to understand this, let us say I take this built-in support first and apply a load here, maybe hang something. Then you know this point tends to go down and this point will tend to move up. As the support pushes the wall down, there is going to be a force, let us say N1, the normal reaction of the wall on the support, and similarly this end is being pushed up. So, this would experience a force N2. Let us go to the next page and see. So, what we did, we are looking at this built-in support, and when I apply a force in this direction, let us say W, at this point there is a normal reaction N1, and at this point there is a normal reaction going in this direction N2. Let us say this distance is B and this distance is A. Then since there is no force in x direction, I need not worry about it. I am taking x direction like this and y direction like this. Summation over f y is equal to 0 gives me n 1 minus n 2 minus w is equal to 0, and summation tau z about the z axis equal to 0. Let us say I take it about this point, although once the forces are 0 it does not really matter. It gives me A times n 1 minus A plus B times w is equal to 0, or n 1 is equal to A plus B times w over A, and similarly n 2 would then come out to be n 1 minus w, or this is equal to A plus B w over A minus w, which is equal to B w over A. So, what we find is for this built in support n 1, n 2, w, we have n 1, this is B, this is A, is equal to A plus B times w over A, and n 2 is equal to B w over A. I could have gotten this answer directly if I took the torque about this point, but the point I am trying to make now is going to be slightly different. I could think of this whole thing, this built in support, as if it is applying a torque at this point at the end in one direction or the other, and a force F, and that is how I want to represent a built in support. Let us understand how this can happen. So, once I have determined n 1 and n 2, this is w. I can add a 0 force at this point, and I choose this 0 force in a particular way. I add n 1 and minus n 1 at this point. Now, this minus n 1, let me use a different color, minus n 1 along with this n 1 gives a couple trying to turn the whole thing counterclockwise. So, this gives a couple at this point in this direction, and this force n 1 and n 2 added together give me a force. So, this whole thing is equivalent to a couple, a moment torque here, and a force n 1 minus n 2 here, which obviously is going to be equal to w. So, what we say for a built in support system is that this is capable of giving a torque and a force at this point. Of course, I could have done the entire analysis about point B, this point near the wall where it enters the wall. I would still say by the similar analysis that this is capable of giving a torque. So, value would be different because now I would be doing things about this point and a force here. So, I can think of a built in support system as providing a torque and a force. Of course, the moment I apply a weight here, this force has to be equal to this, and therefore, weight it has to be equal to w. The length is a plus b, and therefore, this forms a couple which gives a torque in this direction as w a plus b, and therefore, the torque generated at this point to counter this torque is also going to be equal to w times a plus b. So, think of a built in support system as something that can generate a torque as well as a force. You notice that with A plus B increasing, if A plus B is large, this torque is going to be larger and larger and larger. It is actually better understood if we go back to this slide and see if A is large. If A is large, I am talking about this picture. If A is large, then N1 provides a larger and larger and larger torque, and therefore, with large A I need less N1 at this point, and therefore, if you want to have a very stable support, push it really deep into the wall. Let us see now a similar support which is not into the wall, which is not built in, but is welded at the corners. And I apply a load here. Let us see what will happen. As this load is applied, you will see that this has a tendency to turn like this, and therefore, there will be a force generated in this direction. Let us call this N1, and there will be a force generated in this direction. Let us call it N2. Using the analysis similar to what I did just now for the built-in support system, I can again show this to be equivalent to giving a torque and a net force, normal reaction to this load. So, both a built-in support system and a glued or welded system are capable of generating a counter torque and a force, and this is how I am going to represent them. We have not considered x component of the force so far. You know, obviously, if I pull this thing by a force F x, the built-in system or the glued system also generates a force in the opposite direction, because the thing does not come out, and therefore, the complete picture, a built-in support system or a welded system is capable of generating a torque, a vertical force and a horizontal force, and this is how we represent a built-in or glued system. I will do an example of this kind of element, that is a built-in support system which can provide a torque as well as a vertical force and a horizontal force in the next lecture, but let us see what all did we learn today in this lecture. We first completed our analysis or discussion of moments of force, and then we looked at elements, various engineering elements, and what kind of forces they can apply. We looked at a string and saw that it can generate a tension. We looked at a rigid rod, it can generate a tension as well as compressive force. Then we looked at a smooth surface, where we saw that it can generate only a normal force, and a rough surface which I am going to show like this, which can generate a normal force as well as a frictional force along the surface. Then we looked at pin or hinge joints, and this can create a force in x direction as well as in y direction. And finally, we looked at built-in support systems or welded or glued support systems, and saw that these are capable of generating a vertical, a horizontal force as well as a couple moment.